1c. So it says evaluate the surface integral. Really, it's a surface integral, so it's not a flux integral, right? There's two different kinds. You got to use different formulas here. So in this one, we have the double integral or surface integral x ds. S is the part of the paraboloid x equals y squared plus z squared that lies inside the cylinder y squared plus z squared equals 4. Hint, use the rectangular form of ds with x equal to g of yz. I think that requires a little bit of explanation. So normally when you see the surface integral, we have some function of x, y, and z, ds, and then the rectangular form we usually think of z as, I have to change the g here, a function of x and y. So in the rectangular form then, we usually use this formula, the integral of x, y, and then we change z to a formula involving g of x, y, and usually you're given that or you can find that. And then ds is 1 plus, we change to g sub x squared, g sub y squared, dA. So that's normally the formula you use here, except what are we doing in this problem? We're interchanging the roles of x and z, aren't we? But it should still work because the way we choose x and z, it's all arbitrary, isn't it? The formula, if we interchange the letters, it should still work. So in this case then, we're going to use the formula. The surface integral is still f of x, y, z, but now, and then ds. But now we're plugging in x in terms of y and z, so g of y, z here. So then that creates the calculation formula, double integral over r, f of, okay, now you replace x with g of y, z, and then y, and then z. So it's going to have two variables. It's a double integral. It better only have two variables in it if you're in rectangular form, right? Or if you're in really any form. And it's going to be in terms of y and z this time. And then, so what does that make the area element? Yeah. Yeah, so we'll say g sub 1 plus square root of 1 plus g sub y squared plus g sub z squared. Does that seem reasonable to you? So that's the idea. We're just interchanging the roles so that we don't have to resort to the parametric formula, which is a little more difficult to use, I think. Okay, so then do we have to draw this picture, or can we get an idea of what it's going to look like? Let's see. So I'm going to draw the x-axis inside the screen. I'm going to draw as little as possible. But this is a paraboloid, right? The central axis is the x-axis. But the easiest way for me to draw a paraboloid going sideways is to keep the x-axis in the screen. So kind of a rotation of what you're used to. So I'm going to draw it going sideways. So it's opening sideways. Oh, let me try that again. Yeah, not much better. Okay. And then, so what I'm saying is this guy right here is going to be my positive x-axis, which makes my, okay, if we want to keep the right-hand rule in play, then the axis going back into the screen would be positive y, right? And then positive z always goes upward. We never change that, or very rarely anyway. And then what does y squared plus z squared equal 4 graph to be? So that's the positive y back there. Well, yeah, sure. In the yz plane, it would be a circle. So in the yz plane, it's a circle of radius, 2? So I'll go out 2. I'm thinking I'm going to want this to be out 2, too, so I'm taking a chance there because I haven't thought it through. But that's okay. And then this is good. Drawing this is good practice. You have a cumulative final coming up. I suppose you should be able to draw some of these things, right? So a circle, then let me do this circle in blue. But that's really a generating curve, isn't it? For the cylinder, right? Y squared plus Z squared equals 4 is a circular cylinder. Okay. Does that make sense to you? So do we want to draw the cylinder? Well, the cylinder is just going to be a translation of this curve in blue, right? And it's going to intersect the paraboloid somewhere, right? And it should intersect it to where this trace here would be this. It's got to be the same shape as the original generating curve, doesn't it? So I think it would look something like that. Would you buy that? Okay. You might have been able to do the problem without drawing that whole thing, but I think it's helpful. All right, then let's see. So if the x weren't here, say the x were equal to 1, what would we be finding? This is an important, conceptually this is important. If x weren't there, if we were just integrating ds, what would we be finding? It'd be a surface area of which object? It would be the paraboloid. With this is just providing bounds. This keeps it from going on forever, right? It would be the paraboloid from a horizontal, an x position, a horizontal position of where the origin is, right, all the way till you get to here, right? The x just does something else to it. Could be a density function, could be something else. We don't know. It's not going to be surface area though. All right, so let's go ahead and find our partials. So remember, this guy is g, and I made the mistake of saying g sub x out of habit. It would be g sub y we want to find first. What would that be? 2y, and then g sub z? 2z. So then our surface area element ds would be square root of 1 plus 4y squared, you got to square it, plus 4z squared, dA, right? So we need to start setting up this integral then, right? So, okay, it's the double integral. It's going to become the double integral over r. We'll talk about what r is in a second. But what's the x going to become? That's going to be the y squared plus z squared, right? So you got to make that substitution because your integral has to be in terms of y and z now. And then your ds is right here. It's what we just found. It's the square root of 1 plus 4y squared plus 4z squared. And then dA. And now let's go to our picture. What are we going to integrate over in the yz plane? Well, if you project this paraboloid down, aren't you just going to get this disk here? If you think of smushing it down flat. And what? Okay, that's what's the equation of that thing? Well, we've got it, right? It's really the interior technically of that. So y squared plus z squared equals 4 would be the boundary. If you wanted to represent the whole disk, it would be, so this would be x squared, this whole disk then would be y squared rather, plus z squared is less than or equal to 4. So the boundary of that disk is the circle. Does that make sense to you? So, all right, so if you wanted to put that here, you could. Now, of course, what do you want to switch to at this point? Polar. So let's see. Let's put in the RD theta right away so we don't forget the extra R. Now, remember, z is taking over the role of x. So what is x squared plus y squared, or y squared plus z squared? That's r squared right there, isn't it? And then what does this guy turn out to be if you factor out the 4 times r squared, right? So we have 1r out here, no, r squared out here actually, and then a square root of 1 plus 4r squared, right? Any issues with that? We'll simplify that in a minute, of course. Everybody cool with that? All right, and then limits of integration. So without drawing the disk of radius 2 in the YZ plane, what would the R run from? 0 to 2 and theta? 0 to 2 pi. I can separate it into the product of two single integrals, right? So I think that would be a good thing to do. So we get the integral 0 to 2 pi. What's the integrand of this one? It's got to be just 1, right? Yeah, that's the d theta. And then the integral, how does the r stuff simplify? R cubed square root 1 plus 4r squared dr, integral 0 to 2. Yeah? All right, so this part, yeah, easy peasy, right? 2 pi. This one, I think we need to channel our Calc 2, right? Get in the zone, right? Or maybe even Calc 1. You might not have seen this trick since Calc 1, some of you. So I think to start off with, perhaps the obvious thing to do is to let u equal the radicand there, right? So let's actually maybe, you know what? Let's take a timeout. Not that you guys have been bad or anything. This is a good kind of timeout. My son takes the bad kind of timeout all the time. Okay, let's just integrate without limits of integration, because really you're supposed to change the limits of integration if you make a substitution, right? But that's a pain, so I just kind of like to take a timeout and do it as scratch work. So I'm going to let u equal 1 plus 4r squared. Then I'm going to leave space there for a reason. Then what's du? 8r dr. Okay. And I'm actually going to, haven't seen me do this much this semester. I'm actually going to make the substitution. Okay? But if I do that, you're going to see that we haven't covered everything. We haven't covered all our bases. So if we actually make the substitution, I don't have anything to plug in for r cubed, but I do have a square root of u for this guy, right? And then dr would be du over 8r. You see that? If you solve for dr here. So what, do you remember? So, okay, yeah, then we get r squared, I guess, but we still have an r squared there, right? What's the trick that you learned either in Calc 1 or Calc 2 for one like this? In fact, we can find r squared, right? And that's what we need, because this reduced to r squared, that factor in front there, in front of the radical. So let's do that. So from this equation, what does r squared equal? U minus 1 over 4. And so then my idea is to plug this guy in play. This is r squared right here, so we just make that substitution. Then everything's in terms of u, which is sweet. Okay, let me get some more space. Okay, so what does all that lovely stuff become then? Well, okay, let's bring the denominator to the outside. What's the denominator going to be? It's going to be 8 times 4, right? So 1/32. And then what's left inside? Just the square root of u? Is that right? I shrank it too much. I can't see it on my screen. So I'll put the u minus 1 right here. Now do you buy that? Okay. And then it's not that bad, is it? Just what do you have to do? Distribute. So 1/32. Okay, u times u to the 1/2 is u to the 3/2 minus u to the 1/2. And then we integrate 1/32. Let's see. It's going to be, the exponent's going to be 5/2, and then out in front, 2/5. And then minus 3/2 with 2/3 out front, like that. Are we good? Now, okay, back to where we were at over here. Time in. It's important to write that down, right? No, it's not. But if it were important, it would only make sense to put it right there. Okay. So now we go back over here and, okay, so we did everything but evaluate it from 0 to 2, right? We have our antiderivative, in other words. Let's replace u with 1 plus 4r squared. And, well, what do we get? So let me put that 1/32 out front. So the 32 in the denominator right there. And then 2/5, 1 plus 4r squared, that's u to the 5/2, minus 2/3, 1 plus 4r squared, the whole thing to the 3/2, like that. And then evaluate from 0 to 2. Does everybody buy that? Okay. And then, okay, what do we get? So 2 pi over 32 is really pi 16ths. And then what do we get when we plug 2 in for r? So 2/5. That's going to be, what, 17 to the 5/2? I think I copied it wrong. Should have been 4r squared. Okay. Now, what do you get when you plug in 2? Isn't that going to get me 17 inside the parentheses? So 2/5, 17 to the 5/2, minus 2/3, 17 to the 3/2. It's getting ugly. And then what happens when we plug in 0? So this is not pretty at all. Let's see if I can shrink it down a little bit. And then when I plug in 0, it's not going to go away, is it? So minus 2/5, just 2/5, right? Minus 2/3 when I plug in 0. All right, so what's the best way to write this? What's 2/5 minus 2/3? So yeah, this would be 3/15, no, 6/15. If I do it right, 6/15 minus 10/15. So negative 4/15, but then we have a plus here, so see if we can get all this correct. So plus 4/15, is that what I said? Everybody buy that?